This is the last part of the lecture for the second week of IS688, and in this segment we'll be talking about finding frequent item sets. So to place this in context of the larger learning objectives for the lecture, the main two things that we want to discuss here are to look at three applications, or at least be able to describe at least three applications of frequent item set mining. So why is this useful? And then explain the value in counting pairs when we talk about frequent item sets. So first, to provide some motivation, why are we talking about frequent item sets at all? Well, the main idea here is that this problem of trying to find groups of objects that co-occur or occur together often will show up many times throughout the semester. So this particular kind of problem we'll use as motivation over and over again. So we'll see things like using similarity metrics to identify co-occurring items. In fact, chapter 6 of the book talks about this and why you might use that in the context of e-commerce, but the frequent item set mining that we'll do now is more useful in the context of brick and mortar stores. The idea of grouping together users or entities that exist in the same community is a similar kind of co-occurrence problem, where we want to look for quote-unquote communities that frequently co-occur together. And recommendation systems can be thought of as identifying items that co-occur for users who are like a particular user that you want to recommend content for. And then search pages for generating or using search engines to find pages that are relevant to some query. You can also think of as what are websites or pages that frequently co-occur with a given query or exist in a set of frequent item sets. So as I mentioned, this kind of problem provides us a good motivation for a number of the different techniques that we'll use throughout the semester. For this particular idea for frequent item sets, we'll first ground this in a real-world brick-and-mortar kind of example, where we have some supermarket and the managers or the people who run the supermarket want to figure out where to put items, either placing them in reasonable locations for customers coming in or sitting in a checkout line, or for identifying two items that should be next to each other throughout the supermarket, or potentially very far from each other throughout the supermarket. So the approach here is to look at sales data that we can evaluate through our receipt collection from barcode scanners or what have you, to find these kinds of relationships between items that people buy. So the classic rule that people have known or talked about as sort of apocryphal is that people who buy diapers and milk oftentimes also buy beer. And this is a rule that you can essentially mine from these sets of receipts that you collect, that your supermarket collects over long periods of time. As a result, this provides input or decision making capabilities for figuring out, well, if we put beer next to diapers, then the likelihood of our beer sales going up, or we should see a higher likelihood of our beer sales going up because these two objects are generally purchased together. And this kind of thing is common, and we can formalize it in terms of talking about a set of items, which is the things that are sold at a particular store, or things that we're interested in for like movies on Netflix or items on Amazon, friends on social networks. And then we have a large set of baskets. A basket essentially represents a transaction or a small subset of items. So it's not like my full purchase history. Generally, it's thought of as a small collection of things that are purchased together. You can make this like a full history, but the main idea here is that generally the baskets themselves are relatively small. So if we have a set of items like bread, Coca-Cola, milk, beer, diapers, we can look at these in terms of transactions and say, well, one basket is bread, Coke, and milk. Another basket is beer and bread. A third basket is beer, Coke, diaper, and milk, etc. And what we want to do, the objective, is to create these rules that associate objects or associate our items. So the idea being, people who bought X, Y, and Z tend to also buy V and W. That these two things or these two sets go together enough that we should either recommend them or put them close together, or take some action based on this connection. And we can clearly see there's value for this kind of thing in terms of e-commerce, Amazon, recommendation systems, these kinds of things. So what we may see here from this set of transactions or this set of baskets is that if somebody's buying milk, oftentimes they're buying Coca-Cola. If somebody's buying diapers and milk, they're oftentimes buying beer. So maybe you put these things together. We can look at this more generally and say this market basket approach is essentially a mapping of many things to many other things. That this association exists between two groups of items. And what we want to understand are these connections among these items. And there are lots of examples for this that we can go through in terms of product placement in stores, grouping sales or on-sale items with items that are slightly more expensive, or we can offset sale items by increasing costs of non-sale items that are likely to be purchased with on-sale items, and a number of others. So for example, if we're building a store and we have these items being products that we sell and baskets or these transactions being sets of products that are bought in one trip, then we can start to think about this about, well, if we have huge amounts of information about what our customers are buying, if you're Walmart, you have this from just like receipt data that you might collect, then what we want to understand or be able to do is figure out how does a typical customer navigate a store, and we can inform that decision based on the things that they buy. So for instance, if we know that two objects or two items are purchased together a lot, then maybe we want to put those two things together, as I mentioned, so it's easy for the customer to procure them. Or maybe more nefariously, if we know that two objects or two items are purchased very often and very regularly together, then we maybe want to set those two objects very far from each other in terms of store navigation to sort of maximize the amount of time that our customers spend in our store, which is oftentimes why you see like milk is very far away from the produce. Another one that I mentioned is these tie-in tricks for things that are on sale. So if you run a sale on a particular item, you may use that sale to get customers in the door, but you don't want to lose money on your sale. So if you know that people who purchase this item that you're going to put on sale also tend to purchase this other item, then you can lower the cost or put your sale on this first item and then increase the price of your second item to offset this cost. But the whole idea is the rules that we look at, or these associations that we make, need to occur sufficiently often or be frequent enough that we actually gain some money by exerting this additional effort. And you can see this as well in Amazon. The plagiarism example is kind of interesting, where if we look at items as documents and baskets as sentences, then we make this connection between documents that frequently co-occur in a basket. This is kind of a weird example, but if you have a document that occurs in many of these sentence baskets, then that document is potentially risky. So if you know something about these sentences and this object or this document tends to have all these same sentences in it, then why might that be the case? That potentially the sentences were taken or cribbed from some other source, and there's something suspicious about this document. Whereas if it was a non-plagiarized document or an original piece of work, then you would only expect this item to appear very rarely. The drug case is where we have a basket, or baskets represent patients, and the items represent the drugs and the side effects. So when we start looking for combinations of drugs that co-occur with side effects based on these basket collections, then we can start to look at or start to make connections between what these drugs are and their potential side effects. Because we know the space of drugs and we know the space of side effects, that space may be very large, but by looking at where these co-occur, And connecting these pairs of drugs and side effects together, we get insight into what drugs cause what side effects. And there are some extensions make to that as well about whether a particular side effect occurs without a particular drug, which tells us something slightly different, or gives us additional confidence that if this side effect only ever occurs with this drug, then there is some connection there. Whereas if this side effect commonly co-occurs, people often report headaches, often report nausea, regardless of the presence of some drug. Maybe that's some additional or external exogenous factor. The community detection case, I think, is kind of cool, where you look at baskets as nodes and items are the friends of those nodes. And what you want to do is look for these subgraphs in your network that are made up of common groups of outgoing neighbors. So if you have a set of nodes on the left and their friends on the right, then you can start to view these sets of nodes on the right as collections or baskets. And what we want to do is identify these subgraphs that occur sufficiently often, and these buckets can become these sets of items, these item sets can become our communities. That these sets of communities, the largest set of communities that we can get, tell us something about, oh, these people should be connected, or you should belong in this community, and then we can do things around community recommendation, these kinds of questions. So more generally, when we have these many-to-many associations, what we want to do is find sets of items that occur frequently, but not just are frequent. So for example, this is one that we'll talk about in a few minutes. People just often buy milk. People often buy bread. So those sorts of standalone items are obvious or not very surprising from the data. And remember, that was one of the requirements that we wanted for the insights that we find with data mining, that they be non-obvious. So looking for these sets of items, these many-to-many associations that have some constraint, i.e. the occurs with kind of relationship, those are the things that we're looking for. And what we do is what we are trying to do is identify these frequent item sets, that these sets of many-to-many associations are frequent item sets. So how do we formalize this? The frequent item set can be sort of boiled down to a simple question. Let's find a set of items that appear together frequently in the baskets that we look at. We define support for a given item set as the number of baskets that contain all objects in this item set. Generally, we talk about this in terms of some fractions. So if we look at these transactions that we showed before, then we can say the support for the item set beer and bread is 2. It occurs in 2 of these 5 transactions, or 40% of the time. And to look for frequent item sets, we apply some threshold. And then where that threshold comes from is sort of a domain expertise kind of thing. It's based on your use of the data. Though you can set some general kinds of thresholds here, it wouldn't make any sense for it to be less than 0.5, for example. But any sort of, or any item set that occurs or who has support beyond this threshold are in some sense interesting, or at least are not uninteresting, because they may be uninteresting for other reasons besides having high support. So as an example, if we have 5 different items, milk, Coca-Cola, Pepsi, beer, and juice, and we want to look for item sets that occur at least 3 times. So our support threshold here is going to be 3 baskets. So we have these 8 different baskets here. We have a number of different item sets, and then we can count their frequency. So these individual items, M, C, P, B, and J, we can just count up how frequent those are. And we can look for pairs and triples of other item sets as well, and count their support. And what we see are these 7 different item sets that have a support of greater than or equal to 3. So 4 singletons and 3 pairs of items. So we have milk and beer, beer and Coke, Coke and juice. Those occur relatively frequently. But milk and Pepsi seem to be rare. Juice and Pepsi also seem to be rare, relatively. So then we can define these association rules. where we basically create these sort of implication rules that if you have this, then odds are you are likely to have this in your basket as well. So that is, if we have some item set that is composed of these k different items, I1, I2, up to ik, then that implies that we're also probably going to have j in our basket, or j in our item set. So we read this out as, if this basket contains all of these items, then it's also likely to contain j. Now, the interesting thing here is there can be many, many, many association rules, and the vast majority of them are not very interesting. Association rules have been around for a long time, but we can see very quickly the number of association rules that's possible in a particular space of items is very large. So it's if you're doing complexity, it's big O of 3 to the d. It's exponential in the number of items that you have, so this is very large. So for instance, in this example, if you have just 6 items, then you can have 600 odd association rules, and many of those are just not interesting. So we've defined support. We can also define confidence. So this tells us something about how interesting this rule is. So in particular, we define confidence as the proportion or fraction of item sets that include all these items in our item set I, in addition to this item j, or this subset of items j. So if j occurs in all times where we also see items I through k, then that confidence is going to be 1. But not all high confidence rules are particularly interesting. So for instance, the example that I gave earlier, where many people buy milk. So it doesn't really matter what else is in your basket. Odds are you're going to have also purchased milk. So there's some potential explanations for this. One is that there is really an association between the items in your basket, the items that make up this set X, and anytime you are buying that particular set of items, you're also going to have to buy milk for whatever reason. Maybe it's cake ingredients or whatever. An alternate explanation is just that milk is bought all the time. That doesn't really matter what else is in your basket. If you're going to go to the store, you're also going to purchase milk. So this tells you something about, well, this particular milk relationship has high confidence, but it's not really interesting because just milk is bought sufficiently often as to appear as though it has high confidence. So we define an additional metric called interest, and we say this is the difference between the confidence that we have for this object and the likelihood of actually seeing this object. So you can think of this as a way to quantify the difference between dependence and independence. That if the probability of this particular item with or bought with all the items in your item set is essentially the same as the probability of finding this item at all, then these two things are basically independent. And there's no real value there in terms of an association. But instead, if there is some connection, either positive or negative, so if this interest, if our confidence for this association rule is either much higher than or much lower than the likelihood of seeing this item just in general, this item J purchased in general, then there's some connection here that is potentially interesting and actionable. So now we can see an example where we evaluate the association rule for its interestingness. So again, we look at these 8 different transactions or baskets. We have our confidence metric and we have our interest metric. And we can evaluate this association rule of purchasing milk and beer together implies that we'll also buy Coca-Cola. So if we look at the confidence, we can see that there are 4 different transactions that include milk and beer. So basket 1, basket 3, basket 5, and basket 6. And in 2 of those, we also have included Coke. So that's basket 1 and basket 6. So that tells us the confidence is 0.5. And now we can evaluate the interest here, that our confidence will make the math easy, is half or 4/8, and the likelihood of seeing Coke at all is in 5 of these 8 different baskets. So Coke is sufficiently rare. So if we subtract these 2 things, then we get an interest of 1/8, which tells us that really Coke occurs sufficiently often that this rule is not particularly interesting. That maybe really what's happening here is that our confidence in this rule is being driven not by any connection between milk and beer and Coke, but just that Coke is sufficiently common. So what we want to be able to do is find these rules where our item sets are sufficiently common in our data set, and the confidence of this new item set plus some additional item is above some threshold. But the hard part here is not necessarily finding all the possible association rules, because we said there are very many of them, but it's finding that the frequent ones and doing so in a way that doesn't take an astronomical amount of time. So here, if we have some item set I through I1 to IK, that also implies this other item set J, we want something that has high support and confidence. Now, what does this mean? If this association rule holds, then we have two things that we should be able to observe. First is that this item set I, or these sub-items I1 through IK, must be frequent, but also the union of I1 to IK and whatever is in our J item set must also be frequent. Because if that were not the case, then the item set would be uninteresting, which means that this association rule wouldn't pass our thresholds. So how do we find this? The first step is to find all the frequent item sets. For now, we'll just say that's magic, and we'll talk about that in a second. And then once we have all these frequent item sets, we can use these frequent item sets to generate our association rules. So if we have an item set I that has some subset A, and since this item set I is frequent, then any subset of this I must itself also be frequent. Sort of a reassociation of these must also be below some confidence. So that allows us to filter out a number of rules that we don't care about, or a number of rules that are below this threshold. If we have a way to generate association rules once we have the frequent item sets, then really the only thing we need to do is evaluate or find the frequent item sets. So how do we do this? Let's first sort of set up what we expect to have in terms of infrastructure. We have some server that has a log of all the baskets that we've seen on our e-commerce site, for example, where these baskets are these transactions or groups of items that have been purchased together. They're stored on disk. We have this collection that's sort of basket by basket, and critically, baskets are generally small. But we have many of these baskets, and we have potentially many items. So you can map this to the Amazon case, where Amazon has thousands to millions of items that are for sale. But when you go to Amazon, it's very rare that you buy a large number of items. These baskets are these small sets of items that you purchase together. So then the problem becomes finding frequent sets of items, but really this can reduce to finding frequent pairs of items. Now, why is that? Well, first off, there are, because of this idea that your baskets are generally small, baskets that have a couple of items are much more common than baskets that have more items in it. So just the overall sort of dynamics of the system would suggest that when we're saying baskets are small, pairs are just going to be more common. Also, there's a mechanic here that the larger your item set, the less likely you are of occurring. And then in addition, from an observation that we had earlier, that any triple that contains an infrequent pair must also itself be infrequent. That if a triple is itself frequent, then all subsets of that triple must also be frequent, sort of definitionally. So we can say that any triple must contain a frequent pair for that triple to also itself be frequent, which allows us to take some shortcuts in how we find these frequent item sets by focusing on finding frequent pairs. So once we have these sets of frequent pairs, then we can extend to larger sets of items. So first, how do we find these frequent pairs? We need to generate all the item sets of size 2. Now we have to do that because we have to count all these item sets. And if we haven't seen an item set to know that it's, or we haven't counted an item set rather, then we can't know whether it's frequent or not. So you can think about this in terms of algorithms for doing sorting, right? Or finding the max of a number in a set. You have to visit every single item in the set to at least see where it goes at some point. Now, once we have generated all these pairs, then we can say, going forward, we only want to keep track of those pairs that are sufficiently frequent or above our thresholds for frequency. And then we can throw away a bunch of other things that are no longer of value to us. But we have to do that first pass where we look at everything or all these pairs first to make that determination of what can we throw away. So how do we find these frequent pairs? Well, the naive method would be to scan through our entire list of baskets, and then for every basket, we generate all the pairs that exist in that basket. And we can do this as long as the space of items squared doesn't exceed memory. Since we're looking at this n times n minus 1 over 2 case, then we have to build this square matrix of rows of our items and columns of our items, and then populate that matrix with counts of every pair that we've seen. But remember, the number of items that we may have could be very large. So in the case of Walmart, maybe we have 100,000 items for sale. We can do a quick back of the envelope calculation, assuming that we're dealing with 32-bit integers for our counts, then this matrix of counts of pairs could easily be 20 gigs or more. So it turns out we can do better than the naive approach, as one might expect. The first method is to count all pairs using the matrix, but we store half the matrix because the ordering of the pairs doesn't matter. If we have item X and item Y, that's the same as having item Y and item X. And then we can compare that to a different approach where rather than keeping this full matrix, or half matrix rather, we keep a table of triples where we look for only the items that we've seen in our set. Now we have to pay some additional complexity because for approach 1, we only have to store the 4-byte count. But for approach 2, we have to store item IDs, which could be 4 bytes. So we may have to store 12 bytes for every pair that we've seen, plus some additional overhead for this hash table mechanic. So we can do some comparison and say, well, we have 4 bytes per pair for this triangular matrix. And we have 3 times that for approach 2, but we only have to pay that 12-byte cost for pairs that actually exist. So if you imagine that pairs or that the space of items that you have is so much larger that actually the matrix of pairs of items might be very sparse, in which case we can save a lot of memory by not having to store a bunch of zeros for pairs that never exist in our data. And we actually can do this comparison and say, well, with approach 1, if we have 4 bytes per count, we have n squared, order n squared pairs, then we have 2 times n squared bytes if you do the math for n times n minus 1 over 2 times 4. In contrast, for approach 2, where we're doing 12 bytes per pair, but only pairs of counts, or only pairs that we actually see, then as long as we see 1/3 or fewer possible pairs, so if you have the full space of possible pairs, if we only ever see 1/3 of them, or only 1/3 of them, 1/3 of those pairs occur in our data set or our list of baskets, then approach 2 is much better than approach 1. But still, we have this issue of if we have too many items, the pairs don't necessarily fit in memory. So how do we deal with this? Well, the book presents us with the a priori algorithm, and that lets us take advantage of a couple of shortcuts in the data. So the a priori algorithm is this 2-pass method where we can reduce the amount of main memory needs. The way we do this is we take advantage of the phenomenon we showed earlier. We now formalize it with this label of monotonicity, that if an item set I appears at least S times, so does every subset of I. If we flip this, that means if any subset of this item set does not appear in S baskets, then no pair that exists in that set can appear in S baskets. So we can quickly throw out all possible baskets, or rather all possible association rules that do not have any of these pairs that we've identified as being sufficiently frequent. So then how do we find these frequent pairs? So it's a two-pass algorithm that we saw. The first pass reads our list of baskets and counts in main memory the occurrence of each individual item. So as long as our space of items is smaller than main memory, or our space of items times the whatever storage cost for storing counts is less than main memory, then this is fine. And then for every item that appears more than our support threshold time, we count that as a frequent item. Not an item set, but a frequent item. Now for pass 2, we can go back and read the baskets again and count only those pairs that include elements that are frequent. So any pair that doesn't have a frequent item must also itself be infrequent. So we get to skip a lot of possible pairs. So the nice thing, or the complexity, the space complexity of this, is that we only require memory proportional to the square of the frequent items. So if we expect that the number of frequent items is going to be much smaller than the number of total items, then we do well in memory. And this is a useful thing, because you could imagine that if we look at the abundance problem that I mentioned in one of the previous sets of slides, that most things are not of value to most people. So the number of frequent items should be much lower than that full space of the full number of items. So we can save a lot on memory doing it this way. So now we have this question of how do we scale up or extend this method for finding frequent item pairs to frequent item sets of arbitrary size. And we can do this by looking at or constructing two sets. First, we have our candidate set of k tuples. These are our k tuples that can potentially be frequent based on what we learned from the previous pass. So our frequent k tuples in the previous slide would have been frequent pairs that include frequent items. So then for all of these frequent pairs of frequent items, we can count how many times those pairs occur and then evaluate whether that set or that particular item set exceeds our support threshold, and that gives us our set of truly frequent k tuples. So if we look at this graphically, we start off with our set of all items. Now we count all the items in that set, which lets us filter out these non-frequent single items. Now for all pairs, we can look at all the pairs that included these frequent items. Gives us another way to filter. Now we can say, well, of these pairs that include frequent items, let's count those pairs and see if those pairs exceed our support threshold. And then we can keep doing that until we have either exhausted or we've reached k and we have the full k subset, or the full list of frequent item sets of size k, or there just aren't any more frequent item sets, which is likely to happen if k is large. We'll just run out of frequent items before we reach k for large values of k. So what does this mean? That means for each subsequent size item set, or each k, we have to add an additional pass to the a priori algorithm. And then we have, as long as we have sufficient memory to count these candidate k tuples, then we're good to go. For this kind of analysis, the time where we have to spend the most amount of memory is when we look at all of these pairs, because the number of pairs that we'll see are going to be much more frequent than the number of triples or 4 tuples or 5 tuples that we'll see. So the time where we have to deal or consume the most memory is when k equals 2. And then once k equals 3 and 4 and so on, our memory pressure decreases. And there are many possible extensions to the a priori algorithm to identify other interesting kinds of phenomena. So we could look for intervals. We can do hierarchies of products to say, well, item sets that appear sufficiently often, we create a sort of meta item set that is its own item. We can lower the support thresholds that we need as our item sets get bigger. So one of the things that we see is as our item sets get larger, the likelihood of seeing them decreases pretty substantially. So if we want to get larger item sets, then we have to lower our support. But we can build in creating a support value that's proportional or inversely proportional to our value of k. So we have some high support threshold for low values of k and some lower support threshold for higher values of k. And there are a number of other things we can do. But remember, the main idea for getting familiar with this idea of frequent item set mining is that it provides us with sort of a foundation that we can then go back to for a lot of the future applications that we'll do in graph mining or similarity or clustering or these kinds of things. So the main takeaways that I want you to get here are thinking of applications for this frequent item set mining task, and then why is it valuable to count pairs? That this idea of monotonicity, that frequent item sets must also include subsets of frequent items, that all the subsets of an item set, for it to be frequent, must also themselves be frequent. So then we can collapse this down to just looking for pairs, and that ends up being one of the more computationally intractable pieces of this puzzle. And if we can do that well, then we can do a lot of other things well. All right, if you have questions about any of this, please post them in the discussion forums. And that concludes the lecture for week 2.